In the early universe, there was a bunch of hot, dense material. There was also a stylus that allowed me to use the drawing pad, and there it is, I found it. A lot of hot, dense material that was spreading around. We've seen what some of this material would look like from our earlier streams when we were talking about the weak nuclear force and the strong nuclear force. So in the early universe, there appears to be, the universe was filled with what's called a quark-gluon plasma, which we saw before. Quark-gluon plasma is this early phase where it was so hot and so dense that the quarks and gluons were the only things that were there, and photons and electrons and stuff like that. But the dominant plasma, the dominant phase, as far as where the energy was this the quark and gluon field. So the energies were sufficiently high, that the collisions were sufficiently violent, and the densities were high enough that you did not, it was not possible to form protons and neutrons out of it. Here's a question. In the early universe, if a particle is in superposition until detected, then how are there any particles at all, since there would have to have been a detector? So these are excitations in the field. The particle, I guess it depends on which interpretation of quantum mechanics you want to use. So I'm sorry, the particles were still there. You can see the effects that they had on each other. And just because we didn't detect the particle doesn't mean that the fields that those particles come from, so like the photon field and the electron field, weren't there and weren't having those interactions. It really comes down to what are the quantum numbers that those particles would have, and those are the things that you actually detect when you make the measurements. You're detecting, the electric charge or something like that. At least that's how I'm going to wiggle out of that question. Okay, so this quark-gluon plasma in the early universe, it was too hot and too dense to form protons. Eventually, as the universe expands and cools, because that's what the universe does, expands and cools, and then you're able to form protons like this. Protons and neutrons and other particles could exist at the same time. So all of the quarks and gluons and leptons and stuff like that were flying around in the very, very early universe. As the universe expands and cools, you're able to partition the quarks and gluons off into these nucleons, the protons and neutrons. There's still a period of time, so there's these different phases that the universe is going through. So the quark-gluon plasma was really early on, and then we have this, hold on, not what I meant to draw. Here we go, this quark-gluon plasma up to here. So there's this phase transition that happens at what's called the QCD phase transition, where you go from this phase to these particle phases. And this is going to persist for a while, because the next force that's going to take over is the kind of emergent force of the strong nuclear force. So quarks and gluons are early on, then you partition them into these baryons, but eventually the protons and neutrons would like to bind together. However, the binding that you get between protons and neutrons is through the exchange of pions, and that corresponds to some binding energy. So when you bind a proton and a neutron together, you get 2 capital MeV of energy that's released. So that's the energy with which these two things are bound. And if the temperature of the gas or of these early particles or their energy is higher than this, then every time you try to form a proton and neutron binding together, it will be broken apart by the next collision. So you have to wait until the universe cools down below this temperature. Remember that temperature, KT, it has units of energy. And so you have to wait until the energy in the random motion is less than the binding energy of the deuteron. At that point, so that's gonna continue to expand until eventually you get this phase called Big Bang Nucleosynthesis. That is where you're taking these particles and you're binding them together into nuclei. So they start as just bare protons and bare neutrons, and then eventually they will bind together to form nuclei. You can get deuterium, you can get helium-3, you can get helium-4, you can get some lithium and stuff like that. This was way before magma. The temperatures here, so room temperature is something like 10 to the minus 2 Kelvin. Is that what it is? I think that's what it is. Room temperature is 300, not 10 to the minus 2 Kelvin, 10 to the minus 2 electron volts, I think is the temperature, like room temperature. And so this is, what, 10, almost a billion times room temperature. So that's pretty hot. Okay, so here's Big Bang nucleosynthesis. It is the formation of these light elements from the collisions of the protons and neutrons that live around. Now this lasts for a brief period of time, because it's the overlap of the period of time where the universe is dense enough for the collision timescale to be shorter than the neutron lifetime. So the neutrons live for about 10 minutes. All right, and so if the collisions between the protons and neutrons that exist in the early universe, if those collisions happen more frequently than once every 10 minutes, then the neutrons will be bumping into the protons and have the potential to form heavier elements. However, as the universe expands and cools off, expands and spreads apart, the collision timescale between a neutron and other particles is going to be longer than 10 minutes. At that point, the neutrons are going to start to die off, and you won't have any neutrons around to form the heavy elements. The universe is going to cool to the point where you can't collide the protons together because the electrostatic repulsion is driving them apart. And so the neutrons really are the stuff that drives Big Bang nucleosynthesis, and it will turn off not at the 10-minute mark. It will turn off when the density in the universe is diffuse enough so that collisions take longer than 10 minutes. The collision timescale is longer than 10 minutes. This happens at around 10 minutes. There's a famous book called The First 3 Minutes. Other things put it at 1,000 seconds. That's the time scale. Whether it's 3 minutes or 6 minutes or 10 minutes isn't really the important thing. It's on the scale of minutes. 1,000 seconds is 15 minutes. So protons and neutrons are combining together to form deuterium, helium-3, and so forth. And these are primordial stuff that comes through this era. The other thing that's going on here is that you have to have, the density has to be high enough to allow these collisions to take place. The temperature has to be low enough so that successive collisions are less than the binding energy of the deuteron. Otherwise, it will break the deuterons apart. So you have to wait until the universe has cooled sufficiently to allow this to start. However, as the universe is spreading apart and cooling, the other effect is coming into play. So these are two competing effects. In one case, it's too hot, but dense enough to have enough collisions. In the other case, you can end up with it being, once it's cold enough, it might be too diffuse, and so you would never get Big Bang nucleosynthesis starting. You would never form any deuterium if the universe was too diffuse to start with, and so by the time it got to cold enough temperatures to allow the fusion to take place, there weren't any particles left to fuse. So that's Big Bang nucleosynthesis. And then the universe continues along for a while where you have just a regular plasma with the nuclei and the electrons that are unbound. So the universe is electrically neutral, but the electrons are not bound into neutral atoms. Eventually, the universe will cool to the point where the neutral atoms are able to combine with the nuclei, and that corresponds to another phase transition that produces the cosmic microwave background radiation. So these all, again, are caused by what is the ambient temperature and what is the corresponding to the energy of the collisions, and what is the binding energy that is enabled by the force, at that relevant scale. So in this case, with the strong nuclear force, there's a binding energy associated with binding things together via the strong nuclear force, and then you compare that to the temperature, and that will allow some kind of transition to happen once the temperature drops below that threshold. Same thing with neutral atoms. The binding energy of the electron to the proton is like 10 electron volts. So the binding energy of a neutral atom is around 10 electron volts. And so the temperature has to cool down to 10 electron volts before you're able to form neutral atoms. Otherwise, the electrons are going to be knocked off by successive collisions. So here's a question. When the size of the universe is the size of a particle, then the detector, because it can only be in one place, does that sound right? That I don't know. I don't know enough about quantum measurement to be able to really say anything specific about that, or like how that would be interpreted. Okay, so we have this phase in the early universe with the quark-gluon plasma. We form these things through Big Bang nucleosynthesis. All right, Big Bang nucleosynthesis. So these are the things that you can form in the early universe. These are the different nuclear reactions that are going to be taking place. Neutron goes to proton plus electron plus a neutrino. Hydrogen plus a neutron gives you H2, and H2 plus a proton gives you H3, these kinds of things. So these are all the different nuclear reactions that are going to be taking place, and how the early universe would climb from bare neutrons or neutrons and protons combine them together to form heavier and heavier elements. You can imagine getting all the way up to oxygen 16 if there was enough stuff around and if this phase of the universe lasted long enough, which is basically the same thing. If the phase of the universe lasts long enough, then that implies that there's enough stuff around for this to take place. The temperature has to be high enough to overcome some things, but the binding energy to oxygen is less than the binding energy to form deuterium, and so that's fairly straightforward. Anyways, where you get to in this climb, so as you start assembling these different boron and lithium and stuff like that, as you begin assembling them, eventually the universe is going to peter out. It's going to stop forming these things. And so you can draw a line where the amount of time you have to do these nucleosynthetic processes will tell you how far up this chain you fall, or like you're able to climb before you run out of stuff, or in particular before the neutrons all decay. They can't find a dance partner, and so they decay. And that line is actually right here. So from the early universe, we get boron, we get beryllium, we get lithium, and anything lighter than that, but we don't get anything heavier than that. We don't get carbon, we don't get nitrogen. None of these things form in the early universe, at least not in any meaningful amount. Almost everything that forms in the early universe is down here, helium-4, helium-3, and some trace amount of lithium. That shows up in, where is it? In this diagram right here, from the NASA Goddard Space Flight Center, which we will steal because we paid for it anyways. Okay, now what does this do? This says the element abundance. So if you turn your head to the side, it says the element abundance relative to hydrogen. So hydrogen is the line at the very top. That is the density of hydrogen. Down here is the density of ordinary matter relative to photons. So the main thing is that at first we don't know what this value is. We don't know what value the horizontal axis has. We want to find what is the density of regular matter. The more dense the regular matter, meaning the more stuff that there is, the longer Big Bang nucleosynthesis can persist. The less stuff there is, the shorter Big Bang nucleosynthesis can persist. You can even have a situation where by the time the universe cools to the point where you'd be able to have Big Bang nucleosynthesis, it's already too diffuse and you don't get any anyways. So that will tell us the amount of Big Bang nucleosynthesis that took place tells us what the density of regular matter was in the early universe relative to the photons. So the photons we can also count by just looking out and seeing how many primordial photons are there. Okay, so we can make measurements, we can make measurements of these different elements. We can measure the amount of helium-4 in the universe. We can measure the amount of deuterium, the amount of helium-3. If you start with a very diffuse universe, so way, way down here, if this is the universe that we lived in, way down here, so not very much regular matter, then you find that for every one hydrogen atom, for every 100 hydrogen atoms, you would get one helium and one deuterium. That doesn't sound like very much. If the density increases, so we're not changing time, we're just saying here's this period of time. If we increase the density, which increases the probability of these interactions taking place, then the helium-4 abundance will grow. The deuterium abundance will actually shrink because deuterium is fairly easy to burn, or very easy to incorporate into heavier elements. So you'll form the deuterium and it will almost immediately join into something else if it has something else to join to. And so the deuterium abundance will drop. Helium-3 will also drop because it will be converted into helium-4 or into lithium or something like that. So you can see the helium here will drop as the lithium abundance rises. You'll have this lithium here. I'm not entirely sure what causes this dip. It may be that lithium actually breaks apart. It may be that if you have the right density, then you'll have lithium around and it will absorb another neutron and form boron or something like that. Or maybe it will absorb something and split into two. So I'm not entirely sure what this drop is right here. The effects of this drop on the helium abundance would be almost impossible to see, right? Because this is down at 10 to the minus 10, and this is at 10 to the minus 1. So this effect is tiny, tiny, tiny compared to what's going on with the helium. Nevertheless, we can measure lithium. We just can't measure helium to the accuracy necessary to see if this dip shows up in the helium. then what you do is you go out and you measure what is the abundance of helium-4, what is the abundance of deuterium, what's the abundance of helium-3, what's the abundance of lithium. You make these measurements, and that will tell you where these lines, these predictions cross the measurements, tells you what the density of the universe is. So we're actually trying to find the value on the horizontal axis that corresponds to our universe. The way you do it is you make a prediction for all possible universes, and then you go make the measurements, and where those measurements cross these predictions for all possible universes tells you what universe we live in. Here is a question: can the Bright-Wheeler process enable warp accelerations? I don't know what the Bright-Wheeler process is, but it sounds amazing, so probably yes. Okay, if we come back here, there is a plot that shows the measurements. Does this show the measurements? It does. So I don't know who I'm stealing this from. Case Western. Okay, so this tells us the measurements are these horizontal boxes. This is probably like a 1 sigma measurement, something like that. So this is the amount of helium-4 that we measure, which tells us that the universe has to live somewhere inside this box. The baryon density, and this is relative to the critical density, but the amount of stuff in the universe that regular matter in the early universe, or in our universe today, has to lie somewhere in this box. And then you do deuterium, which is a particularly good proxy. If we go back to this other image, the reason deuterium is a good measurement is that it's got a steep decline. And so when you make a measurement, it's able to more tightly constrain the amount, the density. If it was a perfectly vertical line and you were able to observe it, then you would pinpoint the density even better. So the fact that it has a steeper slope than everything else implies that the deuterium measurement is the most important. It has the most information. Anyways, here's the deuterium measurement. The helium-3 measurement has to live in this box. The lithium-7 measurement has to live in this box. And so then you draw a line through all of these different places where the prediction or the measurement crosses the prediction, and that tells you that the baryon density in 10 to the minus 31 grams per cubic centimeter is down here, or as a fraction of the total energy density of the universe, since it turns out that the total energy density of the universe is equal to the critical density, that you get just over 4%. So that is Big Bang nucleosynthesis. The Bright-Wheeler process enable warp accelerations. I don't think so. Warp accelerations, I don't know, that's a Star Trek thing. Warp drive is supposed to be warping space-time, and then you move along through, like you punch through space-time. I don't know, it's some kind of physics lore that's not real. Okay, so that is Big Bang nucleosynthesis. Once Big Bang nucleosynthesis happens, you have a period of time. That happens in the first 1,000 seconds. So in the first 1,000 seconds, all of the deuterium was formed in the early universe. Right now, if you take a drink of water, you have 1 deuterium for every 100,000. 100,000 looks like this. For every 100,000 regular hydrogen atoms. So for every glass of water, basically you have a drop that's heavy water. A big glass of water. You have a trash can sized glass of water. There's going to be a drop of heavy water in it. So that's relatively common if you think about it, compared to some of the other elements in the crust. Okay, so that is Big Bang nucleosynthesis. Big Bang nucleosynthesis happens, BBN. It's this period of time from about 10 to the minus 3 seconds up to 1,000 seconds. So it's 6 orders of magnitude in the lifetime of the universe. It's a factor of 1,000,000 to go from 1/1,000th to 1,000. But it's this brief period of time. By our standards, all of the helium, or like the majority of the helium that we see in the sun, came from the first 15 minutes in the life of the universe. That's pretty cool. Okay, so then the universe continues to expand and continues to cool for a long time, but it's still too hot to allow the electrons to bind to the protons. That doesn't happen until you cool to the point where this can take place. That happens at around 6,000 Kelvin, or 3,000 Kelvin, 6,000 Kelvin. What would it be? It would actually be closer to 3,000 Kelvin. So at around 3,000 Kelvin is where you get another transition, and that's where you can take this plasma of protons, or like nuclei and electrons, and you can take the electrons and bind them to form an atom. So now you got atoms. Okay, this is not a sign for nuclear physics, this is a sign for atomic physics. At least that's what we're going to claim in this stream. And so you now form atoms once the universe cools to around 3,000 Kelvin. This is the temperature of the surface of the dimmest stars, is 3,000 kelvins. 3,000 kelvins. Okay, this happens at around 400,000 years. It's just slightly less than 400,000 years with our current understanding of how the universe works. Okay, what happens in a plasma is that when you're in a plasma, the photons, so here's these photons that are bouncing around, light particles, they interact with all of these particles because it's a free electron. It has no energy levels. It has no quantum states that it can jump between. And so all photons will interact with all of the charged particles that exist in here. And the photons can't escape. They bounce around from one to the other. They're taking random directions. And so they slowly diffuse through the universe. So you have this period of time where you're essentially, it would be like living inside of a star. And the photons start in one location and are bouncing around, diffusing outwards slowly. And this is happening everywhere at once. So like some photons over here are also bouncing around. And the typical distance that they can travel is about one solar radius in roughly 400,000 years. That's about how long it takes for light to leave the center of the sun and make it to the surface. So the photons in the early universe in this period between Big Bang nucleosynthesis and what we will call, well, what's called recombination, this period of time, this 400,000 years, the photons are only able to travel about one solar radius in distance. Then you cross this threshold at around 3,000 Kelvin, where the electrons jump down into a bound state with the protons. And now all of a sudden, there are no more free particles around. There are no more free electrons. And instead, the photons are able to stream freely without bumping into anything. And only a small fraction of them will be absorbed by the atoms. Okay, at this point, it takes, let's see, what does it take? Is it like 5 seconds? So in 400,000 years, in 5 seconds, from the time where the photons are allowed to escape, once the atoms become neutral, it takes a few seconds for the photons to travel more distance from their starting point than they had traveled in the first 400,000 years. So they're basically trapped, slowly kind of random walking their way out from a region. Then the universe becomes transparent, and then almost instantaneously, just a few seconds later, they've already traveled a greater distance than they had up to that point. So this happens at, again, the moment here is called recombination, okay, as though they had been combined before. The real term should be combination. It's the first time that the electrons have been bound into neutral atoms, but we call it recombination because it sounds a little better, I guess. Historical reasons. So at that point, you have all these photons that are now free to stream through the universe. As time continues to go on and the universe continues to spread out, there's another thing that happens, and that is you start forming stars. Those stars start to shine. The light from those stars is very bright, and it starts to ionize the universe again. So right now we live in a universe where the gas is ionized again. Most of the gas in the universe is ionized. However, and so one might wonder, then why can we see through it? Because if it's ionized, then that means the universe is a plasma. And with any plasma, like a lightning bolt, you can't see through it. Just like in the early universe, you can't see through the early universe. You wouldn't be able to see very far because the collisions are happening at really short length scales. Today, the universe is hot enough that most of the gas is in a hot plasma phase. So why can we see through the universe? Shouldn't it be opaque? The answer is no. And the reason is that the typical distance between the charged particles is very large. And so the probability of a photon, the optical depth of the universe, is small. It means that the photons, when they leave a particular place, is a small number. Yeah, I think that's what a small optical depth. So the photons can leave a particular place and they don't run into many charged particles. And so they're not redirected. So early in this stage of the universe, when you had this plasma, the optical depth of the universe was really big, and so the particles couldn't run into, they would keep bumping into stuff. But now the universe is very, very, very diffuse. We're in the galaxy, and where we're located in the galaxy, the density of protons is like 1 proton per cubic meter. And a galaxy is an overabundance of protons. So you can imagine the intergalactic medium where you might have a proton every solar system size thing. That's a lot of space for light to travel through without bumping into anything. So There was a period of time after recombination where the universe was neutral. Then the first stars start forming and start to ionize the universe again. But by that time, the optical depth of the universe has gotten so small that light can travel without bumping into anything. We don't have to worry about it. Yes, this diagram is definitely entropic, because it's better to get more stuff on a single plot than it is to have even less. More stuff on plots makes for better figures. Just like when you're working with food coloring, if you keep adding a whole bunch of different colors to see what happens, brown is the best color, clearly, because it has got the most stuff added into it. Okay, so this is the phases of the early universe. We have Big Bang nucleosynthesis, and we can make measurements that tell us about the processes that were going on in the first 1,000 seconds of the universe. And then you go through this plasma phase, then you go through another phase transition where you're combining the protons and the electrons together. That releases all these photons that have been sitting there, and that produces eventually the cosmic microwave background radiation. So over time now, these photons that were released at the time of recombination are spreading through the universe. As the universe expands, these photons are having their wavelengths stretched out, and so we observe them today not as ultraviolet photons, which would have been what they were when they were first emitted, but instead as microwave wavelength photons. So those are the main periods of time in the history of the universe where we can actually get a handle on what was the physics going on at this time. So they're like benchmarks. At this phase transition, we can see what the physics was like here, or we can see what it was like at Big Bang nucleosynthesis. If there were other forces that would correspond to, or other physical effects that came into play later, such as the epoch of reionization, which is where the first star started to shine and started reionizing the universe, that can give us signatures about, again, the physics that was taking place at that moment in time. So every time there's a phase transition, or some kind of, where there's a certain physics that's opened up by a particular energy transition, then we can use that to probe the physics that happened in the past. So if we look at, there's a quantity called the redshift. Redshift is given by Z. Oh man, I hate this thing. So what we're going to look at is the redshift. So there's a quantity called the redshift given by the letter Z. The redshift tells you how much the light has been stretched relative to its nominal value. Redshift is given by the letter Z. And the amount, like the wavelength that something has, so this is like the observed, that's a D. Observed wavelength is equal to the nominal wavelength, so the wavelength that you measure at rest in a laboratory, times 1 plus Z. Okay, so at redshift of 0, which is what we have today, then the wavelength that you observe through some process, so suppose you're looking at a transition in a hydrogen atom. So here's your hydrogen atom, you're looking at a transition from one excited state to another excited state. That's going to emit a photon with wavelength lambda naught. If you're standing where we are today, then you will observe, so like if you're standing on the Earth in a laboratory, then you'll observe lambda naught. However, if you're looking at a galaxy that's far, far away, then when its hydrogen recombines like this, because of someone turns off a light or something like that, it's going to emit a photon of this wavelength, but the universe has expanded in the meantime and it stretches out that wavelength, and it stretches that out by a factor of 1 plus Z. So if you go back in time as the universe is expanding, the farther back you go, the more stretched the light is going to be. And what we can do then is we measure the redshift. You can measure the redshift by looking at exactly these kinds of transitions in galaxies. You can't really do it with stars. You can do it with galaxies. You can do it with clumps of hydrogen gas, whatever it might be. So you can measure the redshift of different things. And that tells you where it is in the universe, because that tells you how much the universe is stretched out since its inception, or over time. So Big Bang nucleosynthesis happened a long, long time ago. Big Bang, that's the Better Business Bureau. Big Bang nucleosynthesis, this happened a long time ago. I'm not even sure what the redshift was at this point. Like, let's say a whole lot. I guess I could estimate what it would be. So, and I can estimate it from recombination. So recombination, so that's the cosmic microwave background radiation. So this was, the cosmic microwave background radiation is radiation that was given off or released to the public at the time of recombination that has since stretched out. This happens at redshift of z equals, it's 1100, but it's around a redshift of 1000. Okay, that happens at little electron volt energy scales. Big Bang nucleosynthesis happens at million electron volt energy scales, which implies that the redshift was a million times higher. So that would be a 10 to the 9, redshift of 10 to the 9 for Big Bang nucleosynthesis. Now, one thing that's important to note is that redshift is not equal to time. Okay, redshift is not equal time. So the spacing in redshift gets closer and closer together as you go back in time, meaning that this is 300,000 years ago, and I'm sorry, 300,000 years after the Big Bang, and this is a few thousand seconds after the Big Bang, and that's not it's not a linear relationship. Redshift, if you go back to like a redshift of 2, redshift of 2 is almost half the age of the universe, I think, something like that. So it's a redshift of a few is half the age of the universe. And then the other half of the age of the universe is from redshift, let's say 2, it might be 3, back to infinity. So while it's related to time, and you can calculate the time, like the age of the universe from the redshift, they're not equal to each other. So you don't want to make the mistake of saying, oh, redshift of 1000 is 1000 times older. It's not 1000 times older. It's a factor of a few older. We are talking about cosmology today. Let's see. There's a question. What's the radiation called when there's a particle travel faster than the speed of light? It's Cherenkov radiation. Yes. Here's another question. Outside of the observable universe, would those objects exceed the band of visible light? Imagine it's not possible then to measure the radiation from those objects. So the reason we have an object, so here's the universe is expanding, and we have some object out here. And the question is this light ever going to reach us? Well, it turns out, no, not anymore. Because the universe is actually accelerating in its expansion, which was not known until about 20 years ago, just over 20 years ago. Because the universe is accelerating in its expansion, there are objects out here that are being pulled away from us. They're not moving through space away from us. Their space is expanding and pulling them with it. They're being pulled away from us such that the distance between us, so here's us in the center, because we are, of course, at the center of the universe. We're certainly at the center of our universe. The distance between them is growing faster, so the space is expanding faster than light can travel through space. The way to imagine that is, suppose you have a rubber band and you have an ant. So here's an ant crawling on the rubber band. Ant has 3 body parts, right? Like a thorax and the head and the abdomen, something like that. Anyway, so here's an ant. The ant can crawl at a given speed, and you can stretch the rubber band faster than the ant can crawl, which means that you can actually prevent the ant from getting to any location as long as you're expanding the rubber band faster than the ant can travel along it. Same thing's going on here. You have this space, the space is widening, and so light is fixed at a certain speed, and so if the space is widening faster than the light can travel through it, then these are outside of our horizon. Thank you for that subspace barrier, appreciate it. So this, there are objects that are outside of our universe that used to be inside our universe, and the light that they emit will no longer reach us because of the accelerating expansion of the universe. So then the question was, would those objects exceed the band of visible light? So you can, an object that is near the edge of the universe its light would redshift, especially in the distant future, its light would redshift to the point where we wouldn't be able to see it anymore. You can have, because there's nothing that prevents electromagnetic waves from having any arbitrary wavelength, so you can imagine a photon that has a wavelength that's the size of the visible universe. It's a very, very low energy wavelength, but it could be there. Okay, so those are the main stages of the early universe. Big Bang nucleosynthesis, cosmic microwave background radiation produced at the time of recombination, and the epoch of reionization when you form the first stars. The epoch of reionization is still not very well understood. We know that it happened because we can see that the universe is ionized today. We know that stars formed because we're here, and we wouldn't be here if you didn't have a first generation of stars, because we're made out of carbon and iron and things like that, and carbon and iron and things like that didn't exist from Big Bang nucleosynthesis. You can only get up to basically lithium at that time. But the physics of star formation, especially early star formation, is not known. So that's a kind of an area of still early research. recombination is pretty well understood. So let's talk about what happens at the time of recombination. So here's the universe as it surrounds us. So here's our universe. And you have sound waves and stuff bouncing around in the early universe because it's all sorts of things are going on. It's like really rumbly. There's all sorts of quantum fluctuations that are causing vibrations and noise and things like that are going on. So you have sound waves that are in here. Once recombination happens, then those photons are allowed to escape. Sound waves are pressure waves. So you have regions where the pressure has gone up, where things have, the volume, you have a region of space that the sound waves is compressing. When the sound waves are compressing, the temperature goes up because it's adiabatic compression. And so you're going to have regions of high temperature, relative high temperature, low temperature, high temperature, low temperature, high temperature. That's all based upon the size of the sound waves and how the sound waves are bouncing around. So that is going to correspond to slightly different wavelengths of photons emitted from different regions. The low energy regions are going to have what's going to happen is the low energy regions are going to start emitting the light sooner. And so they will emit, because they're low temperature regions, they will recombine slightly earlier. And so the light gets emitted sooner. And so it has had more time to stretch out, and therefore it looks colder. So the colder regions of space are going to have slightly longer wavelengths of light coming from that part. The warmer regions of space are going to persist in their ionized state for slightly longer, which means that they're going to have less time to redshift, and so they're also going to appear hot. So the hot regions initially appear today as also hot regions, like the wavelengths are slightly shorter, meaning that the energy of the photons is slightly higher. So if we were to look at a map of the cosmic microwave background, we could get a temperature, basically. We could measure the temperature of the cosmic microwave background coming from different areas, and that would map back directly onto the surface, the sound surface, basically, of the early universe. All right, here's some questions. Does that mean we are losing observation targets like old quasars? So the quasars that we observe in the universe are too close to us to be affected by this. Things that are falling off the edge of the universe we wouldn't be able to see today anyways. These are they would be way, way in the distance. So nevertheless, even though they might be shining very brightly, that light would never reach us. Another question. I imagine there's a very large window of opportunity to observe those objects. Yeah, so the quasars that we observe, like the most distant quasars, like Redshift 8, something like that? And so I don't even think it's Redshift 8. I think it's like Redshift 6 point something. Let's take a look at that and see. Most distant quasar. It has to be Redshift. 7.5. Redshift of 7.5 is the earliest quasar that we have. So, and that's less than 1 billion years after the birth of the universe, basically. But redshift of 7.5 is kind of still in the early parts of the epoch of reionization, which is kind of like redshift 10 to redshift 6, I think, is the main thing. Okay, but most quasars are even closer than that. They're like redshift. I think they even have them at redshift 2. Anyways, let's see. Excuse me. Imagine there's a very large window. Yes, got that. Is it possible that black holes produce stars and galaxies? Is it possible that black holes produce stars and galaxies? We don't. So no, black holes don't produce stars and galaxies, but they are a process. They do appear to be. Well, there's different ways of forming a black hole. You can form stellar mass black holes. So you can form black holes that come from stellar lifetime, stellar evolution. So you form a big star, that star eventually collapses and can form a black hole if the star is massive enough to begin with. So that is something that can happen. It's a black hole that forms from a star. In the process of forming a galaxy, you apparently also form black holes. And it's not totally clear how those black holes form. If they form, maybe it's a dark matter that brings things together. But we see these black holes in distant galaxies, and they're pretty massive. Like even our own Milky Way has a 3 million solar mass black hole. When you look at just the rate that matter falls into that thing through, like if it was absorbing stars, it would take longer to form the black hole than the age of the universe. And so there's got to be some mechanism to form these supermassive black holes in the centers of galaxies, and we don't fully understand what that is. Because you have to be able to form them fast enough for them to appear at Redshift 7. So it's not clear at this point how you form supermassive black holes. They do form, but it's not clear how they form. Am I Christian? Yes. Is it possible that in theory primordial black holes play a role in this? So we don't know about primordial black holes. We don't know how many primordial black holes there are, if they form, how massive do they form. There are some constraints on primordial black holes that come from what's called microlensing. So there's a project called Mozo Project. Excuse me. So this was looking for massive compact halo objects in the galaxy from gravitational microlensing. And it basically says we don't see any evidence for it. So they constrained the fraction of dark matter that could be explained by these things. There are some windows of mass where primordial black holes there are some windows of mass where this Mozo observation campaign wasn't sensitive to it. So for example, if I think it's 10 solar masses, if primordial black holes are 10 solar masses, then that could be the dark matter, or at least a significant fraction of the dark matter, and it would have avoided detection in the Mozo project. Otherwise, Mozo basically eliminated down to only a few percent black holes that are either more massive than that. Actually, hold on, they would have constrained things that are less massive than 10 solar masses. So 1 solar mass black holes, 1 Earth mass black holes, kind of that range, that's a pretty big range from a solar mass to an Earth mass, but those have all been excluded by the Mozo project. Things that are bigger than 10 solar masses, so like primordial black holes that formed in the early universe that are larger than 10 solar masses, or maybe black holes that formed through the coalescence of something else at 10 solar masses. Bigger than that, what happens is that you would, in the outer halo of the galaxy, so here's the galaxy, here's this halo of stuff around it. In the halo of galaxy, you have binary stars. So you have 2 stars that are orbiting around each other. And there are wide binaries, so 2 stars that are orbiting around each other where their orbital period is gigantic, so they're really widely separated, but they're still bound together. If you had 100 solar mass black holes wandering around, it would ionize these things, it would strip them apart or break them apart. And so the presence of these kinds of wide binaries in the halo of the galaxy puts constraints on the population of 100 solar mass black holes that can exist out there. So anyways, with the Mozo project, if you were to plot the fraction of dark matter that can be explained by Mozos as a function of mass of the Mozo. So these are massive compact halo objects, or black hole-like objects that are going around in the galaxy. They're not made out of regular matter. If they were made out of regular matter, it would have affected Big Bang nucleosynthesis. And so Big Bang nucleosynthesis says that if there are massive compact halo objects that are driving the properties of a galaxy, that orbital properties of the galaxy, it cannot be made out of regular matter. So these would have to have formed prior to Big Bang nucleosynthesis. So you have a range that's like around an Earth mass. It might be bigger than an Earth mass, up to a solar mass, basically 1 solar mass. And you get these constraints from Mozos that look something like this. And then you have this window that looks like this. I think this window is continuing to close as they continue to make observations. But this is like the 10 solar mass window. And then up here at like 100 solar masses, the constraints are pretty good as well. But it only gets down to a few percent, so a percent scale, which means that 99% of the dark matter has to be something besides these, provided that these primordial black holes are not in this window where you can get a larger thing. But anyways, these observations are starting to close off this allowable region. Okay, question. In theory, I read an article saying that there was help from birthplaces of stars and galaxies. It was like 2 or 3 weeks ago. Let's see, I read a paper in Archive, 2 black holes circling each other emitted a star. Well, so when 2 black holes circle each other, well, they might eject a star. So you could imagine having 2 black holes circling each other where there's another star going around the 2, and then as they come in, there might be some interaction that kicks the star out, but this won't form a star. You've already formed a horizon, and when these 2 black holes spiral into each other, they'll just form a single horizon again. hence my name. Oh, that's what I was talking about. I was going to talk about the spaceberry. That's my name. That's your name. I was going to talk about cosmic microwave background radiation. The cosmic microwave background radiation. So we've already seen big nucleosynthesis. This is the cosmic microwave background radiation. These are the bright and cold spots that we see. This is from the Planck spacecraft. Okay, that's from WMAP. This is from the Planck spacecraft. So these are the hot and cold spots that we see from those warm and cold regions from the early universe at the time of recombination. And the distribution, like the typical spacing between hot and cold spots on this, tells us about, basically what are the sound waves that fit in the early universe. They started rumbling at time t equals 0, and then they stop rumbling when you free them up to go wherever. And so you can fit these into, you basically have the type of sound waves you'd get in any musical instrument, where you have one boundary condition here at t equals 0, you have another boundary condition here at 300,000 years, 300K years. And so you can fit this wavelength into that, you can fit this wavelength into it, you can fit this wavelength in and everything else. And then the question is, okay, which ones are most prominent? And so you can count up, all right, these sound waves, how many sound waves are there like this? Like how large of amplitude is that sound wave? How large an amplitude is this sound wave? How large an amplitude is this sound wave that fits in there? And when you do that, it tells you, well, basically, what are the properties of the universe at this point? So when you do an analysis of the cosmic microwave background like this, you basically say, how large amplitude is the sine wave that, or the sound wave that fills up the whole sky? What about half the sky? What about a third of the sky or a quarter of the sky, and so forth? And so you get down to the point where, and here it looks like the most common separation is about 1 degree. So there's 360 degrees to go all the way around right here. And so these dots, kind of the individual dots, are about 1 degree in size. 1 degree is a little bit bigger than the full moon. It's twice the size of the full moon. Well, 4 times the size of the full moon if you want the full solid angle. So when you add up how many, or like what's the amplitude of the wavelengths at different things, you get the following plot. It is the CMB power spectrum. CMB power spectrum looketh like this. Okay, and the most common, like the brightest point, or the most prominent size is right here at 1 degree. And that's that separation that we see here. So the texture, if you were to rub your hand across this, the texture that would stick out the most, that you would feel most prominently, is this 1 degree separation. And then all these other bumps that you see, so the bump there, bump here, bump there, bump there, those are harmonics of that 1 degree. Okay, so half a degree and so forth, like an eighth of a degree here, and etc. So those are the sound waves that fit inside the box from the early universe until today. Or, I'm sorry, from the early universe until 300,000 years, and then you stretch it out to today and observe it. So that is the Planck spacecraft. The COBE, the measurement from the 1990s, first measured this peak. Okay, and then WMAP followed up on that, and now Planck followed up on that. Okay, another mathematic formula pattern, like everything else, exactly. This is, it actually, the physics that goes into producing the model here is actually relatively small. It's sound waves in an expanding universe. You have to account for the fact that photons interact differently, or I should say dark matter interacts differently than charged particles, and so that gives you the asymmetry between, like the reason the bumps don't decline uniformly, that the second one is shorter than the third one, is, I believe, related to the fact that dark matter isn't electrically charged, and so it doesn't respond the same way that the regular matter does that's coupled to the photon. So anyways, what's the temperature gradient in the cosmic microwave background? So the cosmic microwave background doesn't really have a temperature gradient. If you look at the COBE data, CMB, you get the following curve. So this is the spectrum of light taken from the COBE data. COBE was, again, the spacecraft. So here's this right here. This is the cosmic microwave background temperature fluctuations that you get from COBE. Okay, the spectrum of light, which means like how bright is it at different wavelengths on average across the sky, is this plot here. And these, the size of the error bars, the size of the uncertainty here is 400 times. They had to multiply it by a factor of 400 to even see the error bars. So at regular, with the regular error bars, you wouldn't be able to see them. The dots would cover up the error bars. And so 2.725 Kelvin blackbody, it's a 1 temperature fit to these data from COBE. So that, I mean, that's amazing measurement, because they measured the absolute temperature in all directions. The subsequent things, the subsequent missions, WMAP and Planck, they don't measure the absolute temperature everywhere. They measure differences in temperature at different points in the sky. So they basically like, how much is this part of the sky, what's the difference in this part of the sky's temperature to this part of the sky's temperature, and then the spacecraft tumbles, and so they eventually scan the whole sky. COBE actually measured the absolute temperature in all these different directions and produced this CMB spectrum. And that was a pretty gnarly result. This is the pattern that they saw in the fluctuations. In certain parts of the sky, you get a slightly different temperature than other parts of the sky. And then that was improved upon with subsequent data, including the Planck data. Including, where is it? Here, the Planck data. So that is the cosmic microwave background. We can use this information to understand how the universe itself is built, how much total energy there is in the universe. So, for example, what they do is they do an analysis called the 3-point function. I apologize for the very loud noises that are coming in overhead. They do the analysis that is the 3-point function. You basically say, if I connect 3 dots, what are the angles of a triangle to connect these 3 dots? And what is the clumping properties, what's the clustering properties of these bright spots and dark spots in a triangular region? And so that 3-point function determines the overall geometry of the universe. It tells you if you have, so the geometry of the universe is dictated by what happens to straight lines, or what happens to 2 light beams that are starting parallel to each other. If the 2 light beams continue to move parallel to each other forever, then you call this universe flat. If these 2 light rays spread apart from each other, then you call it open. And if the 2 light rays eventually come together, you would call it closed. That's an EE. Okay, so an example of a flat universe is a sheet of paper. An example of an open universe is like a saddle, so something like this. And a closed universe would be like a sphere. Okay, where if you start at the South Pole and you move directly north in 2 different directions, eventually those 2 lines intersect each other again at the North Pole. So these different kinds of universes tell you about the overall energy density of the universe. If you have a lot of stuff in the universe, you can actually close the universe. If the universe was filled with way, way more matter than what we measure, like a factor of 100 more than what we measure, then the universe you would have had the Big Bang, the universe would have expanded for a while, and then it would have come back together and recollapsed. If the universe was open, meaning that the density of regular matter was even less, then the universe would expand forever without bound. So these different, what type of geometry the universe has, triangles drawn on a flat surface, the angles add up to 180 degrees. Triangles drawn on a saddle add up to less than 180 degrees. Triangles drawn on the Earth add up to more than 180 degrees. And so you can do this 3-point function, which is like basically making triangle measurements to determine what is the overall structure of the universe, what's the future of the universe. And it turns out that the future of the universe is this. The universe appears to be flat. The energy density of the universe is equal to the density that it would take to close it, or equal to the density that divides being an open universe from being a closed universe. And so, whoops, not what I meant to do. So what does this tell us? This tells us that the total energy density in the universe is the sum of all energies, available energies, add to 1. So if you were to plot the primary sources of energy density, you would have matter. So this will be, it's mostly dark matter, but it doesn't, this matter is dark matter and regular matter. It's mostly dark matter. And then you also have just energy. So this is dark energy, which we haven't talked about the discovery of dark energy, but this is just energy. If these things sum to the critical density, then the universe has to live on this line. Whoa. Okay, pretend that this is a straight line. Well, that's a really ugly straight line. Come on, you can do it. You can do it. Okay, still not a straight line. Oh, I did it. I ended up at the same spot. Okay, so here's regular matter, and here is, I'm sorry, here's the total matter here and the total energy there. And the fact that the universe is flat indicates that it has to live somewhere on this line. Okay, and so if we can pinpoint where it is on this line, then that gives us the ratio of dark energy to total matter. So we want to come up with ways of measuring the total energy density of the universe and divide it up between the two primary components of dark energy and matter. So we want to have some way of constraining where it lives. The fact that the universe is flat implies that we live on this line, and that comes from the cosmic microwave background radiation. So if you were to say, where does the universe live, and you look at the measurements of the cosmic microwave background radiation, you actually get an ellipse that is almost exactly, it's not quite exactly, but it's almost exactly on this line. It's tilted slightly from second order effects that aren't very important, but it lies almost exactly on that line. So when someone says that the CMB tells us that the universe is flat, it basically tells us that the universe has to live somewhere in this big ellipse that is almost parallel to that line. So we have to come up with other measurements to be able to constrain where things land. One of those measurements is the growth of galaxies. So as galaxies grow over time, they form clumps, and we can measure the location of those clumps as a function of redshift. That tells us the total matter. So dark matter and regular matter. And so we get those measurements. The clumping properties of galaxies give you an ellipse that looks like this. And where these two things intersect, that is the most likely universe. And it happens to land at about a ratio of 0.3 and 0.7. So that's roughly where the universe lives, is 1/3 of the energy density of the universe is in the form of matter, including dark matter, and 2/3 of it is in the form of energy. There is another measurement that was made that we'll have to go into detail later. We can't do it right now. That is the supernova measurements, the discovery of dark energy. And I have a whole video on dark energy. The discovery of dark energy is one where the result comes in like this. Okay, it's almost got a slope of 1. What that says is that if you have more matter in the universe, then you also have to have more dark energy in order to reproduce the results. If you have more matter in the universe would try to recollapse. The fact that the universe is not recollapsing and in fact is expanding implies that you have to have more stuff pushing things apart, and that's what dark energy does. So as you increase the matter, you have to increase the dark energy, and so that's why they're correlated with each other. The CMB measurements say that give you a result where the two things are anti-correlated with each other, and the growth of clusters, growth of galaxies, tells you is something that's independent of the dark energy and is only dependent on, well, roughly only dependent on the matter density. And all of them intersect at a single location. Let's see. There is a question here. Unless the unperceived curvature is in the fourth dimensional space. Well, there's more than just 4-dimensional space. There's, if string theory is to be believed, then it's like 11-dimensional. But we don't see those, right? We only see the large spatial dimensions. Are there limits to the expansion? Let's see. Observation challenge to just measure the curvature of space and be done with it. Well, so that is the curvature of space is done by looking at the cosmic microwave background radiation. I'll show you the picture that shows where these things all land. Would the chance that it's flat be so improbable that it would have to be so precise because one more atom could have tipped it? Okay, so Puzzle Gamer, that's a great question. The chance, like the universe is so flat, why is it so flat? Because it's like right on the cusp of dividing us between two completely different fates of the universe. And the answer to that question is that troubles people. It bothers people that the universe appears to be so finely tuned in terms of the curvature. It's called the Flatness Problem. Why is the universe so flat? It should have picked any number that it wanted, and it happened to choose flat. It could have picked any value between 0 and infinity, and it chose 1. The answer, so that's what inflation is supposed to solve. And we won't have time to talk about inflation today, but I'll talk about it next time. We'll do another thing on this. Let's see. So the probability of it being flat is very improbable, and that's why inflation is motivated as a theory. If light has non-zero rest mass, can it be affected by gravity? Light has non-zero energy, and it can be affected by gravity. It is affected by gravity. Light is affected by gravity. That's what general relativity is. So your coordinate system in general relativity is, you make the statement that straight lines are the paths that photons take. And so if you have some object there, it will deflect photons, and the photon follows a straight line. So what we perceive as a flat universe, or what we perceive as a regularly spaced universe, is a distortion of what the universe thinks is a regularly spaced universe. The universe says, oh, these curved photon paths, that is what the underlying geometry is, and we have to map a regular coordinate system onto the distorted coordinate system in general relativity. Okay, so let me pull up these data, or like these results, and I'll show it to you, and then I'm going to have to take off. Okay, let's see. I'm looking for constraints on dark energy. We'll just do that and see what happens. These are the images I'm looking for, but they're plotted in a way that ruins the story. This is the one I'm looking for. Okay, so this is a flat universe right here. No Big Bang would happen if there was so much dark energy that there wasn't any matter at all, and no matter at all, then you wouldn't get a Big Bang. So the flat universe is the universe along this line, and the cosmic microwave background radiation is almost parallel to that line, right? There's a slight difference between them, but the fact that they're almost parallel, that comes from those hot and cold spots of the cosmic microwave background radiation. The BAO, that is the growth of galaxy clusters, and so it's almost vertical. It's not perfectly vertical, but it's almost vertical. You notice that all of these things are kind of rotated relative to being perfectly linear. So this is almost linear. It's almost got a straight line with slope 1, but it's not quite. Is it slope 1 or slope? It's got some slope, but it's either way, it's the dark matter is correlated with the dark energy, or like y equals mx plus b. So the dark energy is correlated with the dark matter. If there's more dark matter, you need more dark energy in order to explain the supernova. And so all these three independent measurements of the properties of the universe coincide with this concordance model with about 70% dark matter, and 70% dark energy and 30% matter. Matter of any form, dark matter or regular matter. So there we go. That is cosmology kind of in a nutshell. CMB and Big Bang Nucleosynthesis are the two real big benchmarks for the properties of the universe and what we can learn from them. All right, let's see. A few more questions and then I need to run. Imagine globular galaxies. Let's see. Isn't light affected by the curvature in four-dimensional space? Well, four-dimensional space is just time added to the three-dimensional space. And so I don't really know how to answer that question. For string theory, I don't know what dimensions are for string theory. I thought it was like 9 spatial dimensions or 10 spatial dimensions and 1 time dimension. So I'm not sure. Why is the locus of points an ellipse? You mean like, why are these things ellipses? That comes from, so the reason that these uncertainties are ellipses is that it's a first order error estimate. So they make some measurements and that gives them a point and uncertainties, gives them a best fit value and uncertainties in these two parameters. And they only assume a first order approximation to the uncertainty. And so you get ellipses as a consequence. You get the one standard deviation along the major axis and the standard deviation along the minor axis. It's the Fisher analysis, I think is what it's called. You can do more detailed analysis where you produce the posterior sample from Markov chain Monte Carlo, where you would actually see the curvature in the correlation between the parameters, correlations in the error bars, correlations between the parameter and the error bar of that parameter, but that doesn't show up here. So the real universe is the intersection between these principles. Yes, the real universe is, because the universe has to be self-consistent, and so you have all these different independent measurements, and they all overlap in one region. And so you say that the universe has to then be in that region. The universe that we live in has to be in that region. You could have another universe that's down here where you have more matter, but that would slide, all of these things would slide around in order to coincide in that universe. So any universe has to be consistent with itself. it is possible that there's some other physics going on that, maybe would allow certain parts of the universe to behave slightly differently. But the evidence for that, there isn't real evidence that is a large effect. There is some evidence that maybe there are slightly different behaviors in the universe in some directions compared to others, or at some distances compared to others, but it's not something that overwhelms, like it's a detail, it's like a minor discrepancy. So we'll see how it goes from there. If light interferes with itself, can it be accelerated with electromagnetic energy? No, I think you can only affect the photon wavelength by either its interaction with space-time or its interaction with charged particles. Okay, that's what I got for today. So the plan will be on Thursday. We will finish up cosmology. We'll do some of these other topics. We'll see how far we get. We might spill these final topics over into next week a bit further than I thought, and then we'll go on to nuclear energy. So that's the plan. Thanks, everybody. I really appreciate it. Sorry I need to run, but that's the world that we live in.